A technique called Gibbs Sampling, named after the physicist Josiah Gibbs, takes all the evidence into account, not just the upstream evidence. It uses a method called Markov chain Monte Carlo, or MCMC. The idea is that we resample just one variable at a time, conditioned on all the others. That is, we have a set of variables, and we initialize them to random variables, keeping the evidence values fixed. Maybe we have values like this. And that constitutes one sample. And now, at each iteration through the loop, we select just one non-evidence variable and resample it based on all the other variables. And that'll give us another sample. And repeat that again. Choose another variable, resample that variable, and repeat. We end up walking around in the space of assignments of variables randomly. Now, in rejection and likelihood sampling, each sample was independent of the other samples. In MCMC, that's not true. Samples are dependent on each other, and in fact, adjacent samples are very similar. They only vary or differ in one place. However, the technique is still consistent. We won't show the proof for that. Now, just one more thing. I can't help but describe what is probably the most famous probability problem at all. It's called the Monty Hall problem, after the game show host. The idea is that you're on a game show, and there's 3 doors: door number 1, door number 2, and door number 3. And behind each door is a prize. And you know that one of the doors contains an expensive sports car, which you would find desirable, and the other 2 doors contain a goat, which you would find less desirable. Now, say you're given a choice, and let's say you choose door number 1. But according to the conventions of the game, the host, Monty Hall, will now open one of the doors, knowing that the door that he opens contains a goat. And he shows you door number 3. And he now gives you the opportunity to stick with your choice or to switch to the other door. What I want you to tell me is, what is your probability of winning if you stick to door number 1? And what is the probability of winning if you switch to door number 2? The answer is that you have a 1/3 chance of winning if you stick with door number 1, and a 2/3 chance if you switch to door number 2. How do we explain that? Why isn't it 50-50? Well, it's true that there's 2 possibilities, but we've learned from probability that just because there are 2 options doesn't mean that both options are equally likely. It's easier to explain why the first door has a 1/3 probability. Because when you started, the car could be in any one of 3 places. You chose one of them. That probability was 1/3. And that probability hasn't been changed by the revealing of one of the other doors. Why is door number 2 2/3? Well, one way to explain it is that the probability has to sum to 1, and if 1/3 is here, the 2/3 has to be here. But why doesn't the same argument that you use for 1 hold for 2? Why can't we say the probability of 2 holding the car was 1/3 before this door was revealed? Why has that changed 2 and has not changed 1? And the reason is because we've learned something about door number 2. We've learned that it wasn't the door that was flipped over by the host. And so that additional information has updated the probability, whereas we haven't learned anything additional about door number 1 because it was never an option that the host might switch door number 1. And, in fact, in this case, if we reveal the door, we find that's where the car actually is. So you see, learning probability may end up winning you something. Now, as a final epilogue, I have here a copy of a letter written by Monty Hall himself in 1990 to Professor Lawrence Dennenberg of Harvard, who, with Harry Lewis, wrote a statistics book in which they used the Monty Hall problem as an example, and they wrote to Monty asking him for permission to use his name. Monty kindly granted the permission, but in his letter he writes, as I see it, it wouldn't make any difference after the player had selected door A and having been shown door C. Why should he then attempt to switch to door B? So we see Monty Hall himself did not understand the Monty Hall problem.